Okay, so here is my capstone project for statistical programming in Python. For this project, we're looking at OLS, and it's a method for predicting one variable based on one or more other variables. We create a model to do this with a line of best fit, and the line of best fit occurs when the average value of the squares of the residuals is the lowest. So we're trying to minimize that error. And what the residuals are is the difference between the um, line and the actual values. So that's why we call it the line of best fit. It's when there's the least error. And we square those to make sure that they're positive, because deviation in either direction, positive or negative, is equally important. It represents an error. This is particularly useful in a wide variety of fields, and it's good at predicting values of something under hypothetical conditions. So for my specific example, I used a data set on married couples from the UK that I got from Open Intro Statistics. And then I had to mount the drive so that I have access to it. And then I needed to read the CSV file and create a data frame from it. I added in a couple extra columns just so that I have more to work with, because I didn't know at this point uh, what variables I wanted to examine yet. So this just gives me a few extra options. And then it's important when working with data that we remove any NaN or not a number values, because we can't really do statistics with these. They're not numerical. They don't tell us anything. It probably just means that they didn't have data for these metrics. So we can see that there are actually quite a lot of rows containing those, and we're just going to drop all those rows. And then we can look at the basic info on the data. And now that we've removed those not a number values, we call the data cleaned. We say that we've cleaned the data. So then we're going to look at a heat map, which shows the correlations between all the variables. And that just means how are they related. So you got a correlation of one that's as strong as possible in a positive direction. One goes up, the other goes up. Negative one, strong as possible in the negative direction. So one goes down, the other goes up. Zero means they're not related. When we're trying to make um, a linear regression model, we want our variables to be pretty well correlated, because the strength of our model definitely depends on that. An example I would like to use is you probably couldn't make a very good model trying to predict the lottery numbers based off of the weather, because they're not related. They're not correlated with each other. So we have a few options with pretty high correlation. The ones I chose were the highest correlation, which is the age of the wife and the age of the husband. I use the wife's age as the independent or explanatory variable, and the husband's age is the dependent variable. So then I just did a scatter plot. We can easily see a pretty strong positive relationship. Wife's age goes up, husband's age goes up. Um, and then there's another plot that actually shows the ages for each individual couple. So I sorted it by the wife's age, and then we're going by index, so we can see all 169 couples. So at any given index, we see the corresponding values. Um, and then we're going to use the stats models.formula.api library to create our regression model. We put the dependent variable, then a tilde, then the independent variable, and we use the dot fit function. Now, printing out a summary of this model, we want to check a few things to make sure that this is actually a good model. So we check the p-values of the slope and intercept, and we can see that they're well under 5%, which is our significance level. So the slope and intercept should both remain in the model. They're significant. The r squared value tells us how predictive this model is, and it's 0.882, which means that 88.2% of the variation in the husband's age can be explained by the wife's age, and that's a strong correlation. The F statistic, we want to look at the p-value, which has a very uh, it's a very low number. So it's much less than alpha, and we have significant evidence to reject the null hypothesis that the coefficients are zero, which means that we can assume that these coefficients we came up with are probably correct based on all of this information in conjunction. Now, looking at the information about the fitted regression model, we want to calculate b hat and m hat, and then we want to find the fitted y hat values, which are going to be the predicted values at any given x. So we have the wife's age. Well, what do we predict based on that the husband's age would be? That's what the y hat is. And then we have the error, or the e hat, which is the difference between our predicted values and the actual values. And then the sum of squared errors is what it sounds like. Basically, you just square each error and then you add them all together. The standard deviation basically tells us, on average, about how much can we expect the actual values to deviate from the predicted values. Now, let's graph the regression line with the data, including residuals and error bars at 2 standard deviations, both above and below. Doing this, we can see that there are definitely some outliers, but we want to be more precise, so we'll use a numeric method. Looking numerically, we can see that there are 8 outliers, 5 above and 3 below. We need to remove these, and so we just drop those. And then I wanted to reset the index so that we're still working with the same indices. So then we got to regenerate the model without the outliers. And then we need to perform the same stuff again. So we got to check to make sure it's good, check the p-values, check the p-value for the F statistic, check the R squared. Everything's good. It's gotten a little more accurate because the R squared is higher. Then we got to recompute all the fitted values. And then we want to look again at the plot. We can see that there are still some outliers. They're pretty minor, but we might as well and go ahead and remove them again. So after doing that, we just repeat the same process. And now we can see that any outliers there are, I mean, there are a couple maybe, but they're very minor. And at this point, we've already removed outliers twice. I think it's probably okay if we leave these really minor outliers in the model, especially because I actually did go ahead and go through the whole process again, and there were still these really minor outliers. But I don't know how many times we'd have to go through it to remove all those. And, I honestly don't think it's going to affect the reliability of our model that much because they're barely outliers. And I don't know. I feel like maybe there's a fine line between removing too much data and trying to get rid of outliers. I'm not convinced that these are like true outlier values. So I chose to keep those in. And then we need to check our assumptions. We make 3 main assumptions when we're performing a linear regression. And these are independent errors, normality of the residuals, and homoscedasticity. So independent errors refers to the idea that when there are errors, they're not correlated with each other. So we use the Durbin-Watson test for this. And we want a value about 2. It ranges from 0 to 4. We don't want to get a value near 0 or near 4 because those would indicate a serial correlation, which would violate independent errors. And upon checking, we have 1.862, which is about 2. So there is probably no serial correlation. And that means that the errors are probably independent, which is good. For normality of the residuals, we use the Jark-Barra test. and it has a p-value of 0.259 in this model, which is significantly greater than zero point zero 0.05, which is the significance level. So we can reject the null hypothesis, which means the assumption of normality of the residuals still stands. And then for homoscedasticity, we look at the p-value, which is definitely greater than our alpha. So we fail to reject the null hypothesis of homoscedasticity, meaning that we do support the fact that the model has homoscedasticity, which is good. Now, these are just some plots that can help us visualize the assumptions. We can see that the residuals are pretty randomly distributed, and there's no clear pattern. They kind of cluster around the horizontal line, so that's good. We want the distribution of the residuals, like their values, to be about normal. So a lot of them around 0 and less at the endpoints. And we can tell that that's mostly true. It's pretty normally distributed. It doesn't have to be exact, but it's close enough. And then here's our QQ plot to also look at whether this data could be from a normal distribution. And looking at this, I would say it's probably good enough for our model. Okay, so here's just one final visualization of our model. We can see that it's actually pretty accurate because the green represents the predicted values, whereas the blue represents the actual values. And I would say it's pretty good. We can see that the actual values are very clustered around the predicted values. So that's just one more demonstration of how great linear regression is. Thank you for watching.